Hi there, welcome back to the formulaic approach. Now in this video, let us talk about the electric circuits. We want to talk about current, voltage and resistance. Alright, and I promise you by the end of this video, you will be able to understand what they are specifically because I'm going to explain it as simplistically as possible, okay? Alright, so first, what is an electric circuit? Electric circuit simply means the path that is provided for current to flow. Is that okay? So the path that is provided for charges to move around. Is that okay? It's always a closed loop. Do you understand? So we say a circuit is a closed loop provided, closed loop, which is a path provided for charges to move. Okay, now there are different types of charges. Before we talk about different types of charges, let's not talk about the components of a charge of a circuit. I said there are different types of circuit rather. Now let's now talk about the components of a circuit. What are the things that make up a circuit? So we have the voltage source, which is battery. The battery is the one that supplies energy. Okay, so we're going to be talking about voltage. We have the wires itself, the wires, okay, or conductors that make up the largest part of the loop. And then there is the switch that completes the circuit. It completes the circuit. And we have the load, okay. The load could be a resistor, could be just something that uses up energy. So this one uses up the energy. So the energy provided is the voltage. Is that clear? All right. So we already know these are the components of the circuit. Now, what does a typical circuit look like? A typical circuit looks like this. So it looks something like this. Just follow me, okay? So we know this is a circuit. Now you might be thinking, why do we draw it like this? Now you should also know that, okay? There's a reason why we draw it like this. Now this thing you are seeing is just one long wire, one straight wire that connects so if this is a battery, I use a wire to connect this end to this end, then current can flow. Is that okay? Now, so this guy here that you are seeing here is the electrical symbol for battery or a cell. This is a cell, okay? So when we connect batteries together, I'll talk about that, okay? I can have two batteries here. So the way we do that is we use dotted lines. We connect them end to end like this. So this is a battery, meaning that it is more than one cell that is there, more than one cell. So a cell is one battery, think of it that way. Then a battery is many cells together, right? So now, so this point is the positive end of the battery is negative, positive end of the battery, negative end. So you can see that we connect them positive to negative, positive to negative. Exactly. So we use dotted line to show that they are connected end to end. This straight wire here, this straight line here shows that they are wires. So it's not wires that connect batteries together. Exactly. Then there is a load here, which is in this case a resistor. Now, what happens is that this guy supplies energy for current to flow in through this circuit. Now, the current that is flowing, what is current then? So, what is current? Current is the flow, rate of flow of charge. Current is what? Rate of flow of charge or charge flowing per unit time. Is that clear? Is that clear? So current is generated by I. So we say I is equal to what? Q over T. So this current. Now, current is simply, so once electrons begin to move here, we call it current. Okay, then you now ask me that, does the current emanate from here? No, the current does not emanate from negative here. Current emanates from negative here. Oh God. You ask that, do the electrons are the one moving here. Exactly. Electrons are moving here. in this direction. But electrons do not emanate from here. Okay? Electrons actually are already on this wire. Free electrons, I've explained that before in my previous video, so I'll link that in the description. Free electrons are not here. Free electron, it's not like electron is coming here, it's from here, it's now coming like this, and like, no. These guys are already, there are already electrons on these guys, on the wires throughout like this. Okay, but they are immobile. Why are they immobile? There is no energy. Exactly. So there is a component here that we call the switch, right? So the moment we close this switch, once they touch, it means we have closed it. Then it means you have completed the circuit. Then what will happen? Current begins to flow. Current flows from positive to negative. So current flows from positive end to the negative end. But electrons, the path that electrons move is negative to positive. Then you now ask, but we say that current flows from positive to negative, and electrons move from negative to positive. Why is direction of current not direction of electron? Actually, the convention was used because it was later that it was discovered that it was electrons that were actually moving, that constituted in current. Okay, but it made sense, but they didn't change that convention, that conventional current flows from positive to negative, because it makes sense to say that if negative charges, which are electrons, are the ones moving from negative to positive, which they discovered, then it makes sense to say that positive charges are the ones that will be moving in the opposite direction. So that's why it was not changed, that conventional current moved from positive to negative. Is that clear? So like I was saying, this battery here is just to supply energy for these electrons to move. When the circuit is open, there are electrons around these wires, around this entire thing, there are electrons, but they are immobile because there is no energy. The moment you close this switch, you close it, what happens is that this guy provides energy for these guys to move. Okay, so now this battery here, let's say it is rated 6 volts, for example, or let's say 6 volts, for example. Now, what this means is that each electron here, or each charge, let's talk about it in terms of positive charges here. Like I told you, a current is defined in terms of positive charges. Is that clear? That is, it flows from positive to negative. So I'm saying that now that each of these charge that is flowing from positive to negative will be giving 6 joules of energy. Remember that voltage is work done per Q, right? That is energy that is given to each unit of charge. Energy that each unit of charge has. That's why voltage is also measured in coulomb per watt, joules per watt per coulomb. Okay, so what this means, 6 volt of battery, means that each charge here will get 6 joules of energy per unit charge. Is that correct? Each of the charges will get 6 joules of energy. 6 joules of energy will be supplied to each charge. That's the meaning of this thing here. To each unit charge. Do you understand now? Alright, so that's what this means now. Now, if that's the case, then what is now current in terms of this guy here? Current is how the rate of flow of those charges. Now, for example, if I put a 12 volts here and I remove it and a 6 volts, I remove it, I change it to a 12 volt or a 10 volts. Now, the energy that this one will give is 10 joules for each charge. What does that mean? It means that the rate of flow was more than the rate of flow when it was 6 volts of battery. So it means that 10 volts, so the current is the rate of flow of those charge. Makes sense? So the current will be higher provided that the voltage is what? High. So that's what Christian Ohms found out. So we call it Ohm's law. He now postulated the Ohm's law. That the voltage across the two ends of a metallic conductor is directly proportional to the current flowing through the metallic conductor, provided that the physical conditions like temperature and other conditions are kept constant. So it means that V is equal to Ki. In this place, our constant is resistance. So V becomes IR. Exactly. So V becomes what? IR. And remember, we already said here that V is also what? V is also what? Energy per unit charge. Okay. Now, what is now the third component I want to talk about? The resistance. I'm going to relate everything. Okay. But now let's not talk about the resistance. Now, the resistance is the opposition to the flow of current. Resistance is what? The opposition given to the flow of that current, that flow rate. Do you understand? So think of it as when you and your father are moving along a path in a car, for example. So let's say this is your car, so this is your father's car, and you are moving on a road. So your father will speed up, provided that the road is fine. So he will speed up the car, and you even be telling that is slow down, that is slow down. Okay, so that will speed up. But when it gets to a path that there are stumps, there are roadblocks, you will begin to try and maneuver his way. He can't speed up here, right? So that maneuvering of his way that is trying to find the path there is called resistance, because it is an opposition to the speed of the guy. Just like it is an opposition to the flow of current. In this case, flow of current. Exactly now. So resistance is given by V. Resistance is given by V over I from that equation. Is that okay? We are going to talk about each of these components separately in a later video. But I want you to understand their relationship entirely. So these ones here are the conductors. The switch here is this guy. The load is this guy. Now you see, another component that we have to talk about is now with this resistor. Now, we usually measure the energy that it consumes, okay? So we said that it is the opposition to the current, right? What does that mean? It means that as this car is trying to, in this case is signifying the flow of the charges. As this car is now trying to find this path, it becomes slower, right? So in this case, we are saying that it has used up some energy with the electron. It will use up the energy that the electrons are coming with. Do you understand now? So for an ideal battery we are not talking about the normal battery, the real life battery. This is not the case. But for an ideal battery, an ideal battery is one that has no internal resistance. That's an ideal battery. No internal resistance. So since it has no internal resistance, it means that if you call that battery 6-volt battery, it will supply exactly 6 volts to every charge that is flowing. So let's say in that ideal case, we will now consider the ideal case in physics. It will supply 6 volts exactly to each electron that is moving. So as the electron begins to move, when they flow across here, they will lose all of that 6 joules of energy. Exactly now. Okay, so to measure that, we always put a component across this. We call that component a voltmeter. So a voltmeter will now help us to measure the voltage across this point. Exactly. So we call that potential difference, and that brings us back to voltage. There are different names we call voltage now. Voltage can be called EMF or potential difference. Now, what's the difference between them? They're actually different. They both refer to voltage, but you see, this potential difference is the voltage difference across 2 points. So that's why we connect a voltmeter across the resistor to measure the energy that is provided for electron at this side of the circuit relative to the energy that the electrons have at this side. So it means that all of those electrons, as they flow past in this direction, for example, since electrons are not going in direction, they will lose, if it is 10 volts of battery, that's 10 volts of battery here. For an ideal battery, this 10 volt of 10 volts rating means that it will give each electron 10 joules of energy per charge. Each charge will have 10 joules of energy, and they will lose all the 10 joules in this place. Is that clear? For an ideal battery. All right. Now, so the potential difference across this end here is what we call the voltage across this end is what we call potential difference. Now, when do we use the electromotive force? Electromotive force now comes when we have a real life battery. Now, for a real life battery, there is also, you notice that after you use your phone or your device for a while, your battery begins to heat up, right? Yes, the reason is because there is internal resistance that causes loss of energy too. Okay, so it means that there are two types of resistance. There's internal resistance and there's what? External resistance. So that internal resistance is the opposition to the flow of current within this battery. So we have internal resistance and external resistance, like I said. I'm trying to explain electromotive force now, how it is different from that voltage. So electromotive force makes us to know that there is also internal resistance and there's external resistance. So internal resistance, we'll call it R. External resistance, we'll call it R. So it means that if there is an opposition to the flow of current within the battery, of course you know within the battery, for example, in a voltaic cell and a galvanic cell, we use a battery to connect, a wire to connect one electrode to the other. So there are two electrodes. So that wire also has its own resistance. I'll talk about all these components separately, but I just want to, for those of you that already know a thing or two about these things, that's what I'm trying to explain this to. So this one, there's a resistance that is caused by the, there's a resistance that is caused by the nature of this battery. So that resistance here is going to be called internal resistance. It's usually very small. Okay, but for an ideal battery, there's no internal resistance and there's no ideal battery. But for a real life battery, there's internal resistance, which also impedes the voltage of the flow of current in the battery. Okay, so it means that the electromotive force is actually, we call it EMF for short. So in this case, electromotive force, I didn't write it before, electromotive force, okay, electromotive force. Now we denote it by E. It's going to be the voltage that the battery eventually supplies. I'm going to teach you how to calculate that now, and I'm going to use an example. The voltage that this guy supplies, so let's call it voltage external, plus the voltage that has been used up internally by the resistance posed to current inside this place. Is that clear now? So this voltage here is going to be IR. That is voltage with resistance, being that this external resistance is bigger, plus the voltage that is inside here. Now it's going to be IR too. Then you now see that the current I is not changing. Yes, it's because when you connect something in series, when you connect resistors in series, it's the same current that flows through them. Just think of it as a continuous conduit for pipes, a continuous pipe. It is the same flow rate that they will experience. Flow rate in one end will be equal to the flow rate in the other end. If you remember, in flow rate, Bernoulli's equation. Continuity equation tells us that the flow rate in one end of the pipe will be equal to the flow rate in the other end of the pipe. Is that okay? Even though the area is different, the volume is different. Does that make sense? The flow rate will be, so current is going to be flow rate. So it makes sense to say that the current inside this place will be equal to the current inside this place. But the resistance are different because this one is internal resistance, this one is external resistance. But the EMF that is supplied in the entire circuit is going to be the voltage of external plus voltage of internal. So it means that EMF is actually the measure of the total voltage. EMF is the measure of the total voltage in the circuit. Is that okay? So since current is the same, E equal to I into brackets, capital R plus R. So in this case where we are supplying, our battery is rated 10 volts. If our battery itself has internal resistance of 2 ohms, for example, resistance is measured in ohms. That was one thing I was supposed to say. Resistance is measured in ohms, denoted by omega. Voltage is measured in volts, and current is measured in ampere, denoted by E. Is that okay? Now, so I said this resistance is internal resistance. This resistance outside there is the external resistance. So let's say this external resistance is rated 1 ohm. I know it should be more than this. So let's call this internal resistance. Let's call it 1 ohm. Let's call the one outside 2 ohms. Now, if the current flowing through that this thing can supply is actually 2 amperes. No, what are we now looking for? We want to look for the voltage across, we want to look for the voltage across the external resistance, across the external resistor. We want to know the voltage across it. Remember that I said just now that E is the formula. E is voltage in external resistor plus voltage in internal resistors. Internal voltage through across the internal resistor. So the total EMF, we know that is 10 volts. E is 10 volts. So 10 will be equal to V in external will be I times R. What is I? It's going to be 2 because it's to be current throughout the entire guy. So current into brackets, the big resistor, voltage in external resistor will be 2 times external is rated 2 ohms. Oh, we already know it. We can calculate it. How do I do that now? Okay. For us to be able to calculate the voltage across this, it means that we need to know the, if we are not giving the resistance of this guy, then let's say we don't know the resistance, okay? Then we'll say that E will be equal to V plus IR. Does this make sense? So if E is 10, then the voltage in the external will be equal to, this will be plus IR. I in this case is 2 and the internal resistance is 1. So the voltage in the external resistor will be 10 minus this, 10 minus 2. That becomes 8 volts. So it means that the amount of volts that is delivered to this external guy is actually 8 joules per coulomb. Do you understand now? So in real life, external resistance will be subtracted. Internal resistance will be subtracted from the total EMF that this guy can actually supply. So if I rate a battery 10 volts, for example, that 10 volts will be equal, the total EMF it will supply, the voltage it will give that resistor, maybe that will enter your bulb, for example, our resistor bulbs, is going to be the total voltage that it can supply EMF minus the internal resistance. Is that clear now? So this is what happens in the real life, in real world. All right. Now let's talk about, we've talked about Ohm's law now. So there are things that obey Ohm's law. We call them ohmic conductors. And things that don't obey Ohm's law, we call them non-ohmic conductors or non-ohmic resistors. Ohmic conductors have the standard graph of Ohm's law is like this. That's voltage against current. So the resistance is this. So the slope of the Ohm's law, the slope of VI graph is resistance. Is that clear? But what if I now change this graph like this? I have I here, I have V here. So the slope of this graph is going to be inverse. That's what? I1 over R. Yes or no? So the slope of an IV graph is going to be inverse of resistance. Right? So this for ohmic conductor, you will see that it's a straight line, showing that as the voltage is increasing, the current is also increasing, or as the current is increasing, the voltage is increasing, meaning that the resistor is using more and more energy up. Do you understand? It's using more and more energy, Okay? So now, like I was saying, what if we now have non-ohmic conductors? What are now non-ohmic conductors? Example of ohmic conductors, we have our metallic conductors like Constantine wire, etc. like that. But if you have non-ohmic conductors, things like diode, like thermistors, bulb, filament, etc. These are non-ohmic conductors. They are all what? Non-ohmic. It means that they don't obey Ohm's law. Ohm's law is saying that the current should increase as we increase the voltage. But what is happening with non-ohmic conductors is this. we see that their graph looks something like this. For example, let's pick for a diode. Okay, so um, the voltage starts up from almost nothing. All of a sudden, it just picks up. Yes, it picks up, and the voltage just picks up. It means that the current, with even the low current that is supplying, it picks up. Just in case you don't know what a diode is a device that can supply current in only one direction, and that direction is called the forward bias direction. The forward bias direction. Okay, so that's why you can use a diode to convert AC to DC. But we'll talk about that. I've talked about that in my previous videos. Just check on those videos. So, but you see, this guy is a non-ohmic conductor. All right, so you see the graph is not telling you go straight like that. Yeah, look at a bulb, for example. A bulb, the VI graph will look something like this. So for a while, the voltage and current will be working together. After a while, what will happen is that it will pick off too. Is that time you begin to see the bulb is heating up. So by that time when it's heating up, it will not supply the Jesus is Lord. It will not supply the needed amount of current. It will not supply more and more current, but the voltage that it will be using up a lot of energy. Even with the low current, relatively low current that is supplied. So this is a non-ohmic conductor. Is that okay? So that is basically it for this video. Do want to subscribe to the channel and click the bell notification. I'll talk about this component of this thing separately and hopefully solve questions for you. God bless you.